Thank you so much for the introduction. I hope you understand me. I hope you see my slides. If not, please tell me. Yes, my topic was introduced. I'd like to mention I'm of the School of Chemical Engineering Advanced Materials, and I'm the Research Director of the Andy Thomas Center for Space Resources. I'd like to introduce a bit what we are generally doing. I'm an editor-in-chief of a journal, Space Exploration, so I'm also very passionate about humans in space and how that might go on. We just made this book over here, which you see here physically. This is made together with the director of Axiom Space for in-space manufacturing, which is Jana Staudemeyer, and the lead geologists of all JAXA missions, so all these asteroid missions, which is Diego Miyamoto, who just visited us 2 months ago. And then there's Ian Fisk, with whom I share a lot of students, as you will see on the next slide. Maybe what we do, I will report here about an Australian-led ISS NASA experiment. I'm aware that very few experiments were made before, but to our best knowledge, that is the first Australian-led ISS NASA experiment. If not, it's the second or third. We have a new ISS experiment in preparation. I also do something with a NASA researcher on the Venus exploration program. I'm very happy that the US school chose me, and not a US researcher, for their submission to the students program. So as a previous speaker, I'm very passionate to all kinds of students, high school students. The students I talked to, I think they were 8 years old or so. It's very nice to see those students thinking about space experiment. And in this sense, I also
Sorry, Dr. Hessel, we seem to have lost you there. I'm not sure exactly what to do here.
Some of them are shared with the University of Nottingham, so they are on food and farming. Now, I'm a chemist by education, and I'm a chemical engineer by working, and I like to advocate a bit for chemical engineering in space. I think what is called ISU is usually done in a very narrow definition. It's on oxygen, on hydrogen, water, on the batteries, and a little bit more, even if it is food. But I think there's much more chemical engineering needed. And NASA and the American Chemical Society, they formed now a group which is called Space Chemistry, and I'm part of that. And that you can see what space engineers can do. Anemi Bongas, who's one of the best in our field, he made a fast experiment on oxygen production with plasma technology, which is advanced. And that is original, cited from our papers, because I don't want to bias it. He found 30 times more oxygen than NASA has found with their MOXIE system. So this shows what chemical engineers can do. Naturally, more on the traditional side, we can work on making new molecules, on space mining, hydrometallurgy, on supply chain engineering, closed loop engineering. But as the previous speaker, or the 2 previous speakers, I like to mention that we can do much more. And we work a lot with our agri-food colleagues at WAIT. So we make astronaut beverages, which I've talked about last year, and we make them under microgravity conditions with one of those mentioned random positioning machines, the Airbus 2.0. We make fertilizers for aeroponic farms in space. We have space medicine, that's what I talked about. And I will end with digital twin systems engineering for space food. Now we have a nice artist, which makes the images. And initially I thought this is just a comic, so not too much science, and I would not have shown it here. But when you make such a kind of vision, how a chemical factory on Mars should look like, then you get some ideas about system engineering. So those images really help a bit, and it helps also to make clear what we're actually heading for to other people. In this sense, we made a review paper on catalysis in space. There's so much done in catalysis in space, and this is given in the anniversary issue of chemical catalysis today, which is one of the best catalysis issues. And there's a look for the future of catalysis, and luckily they found it important that somebody writes about space catalysis. And I and Katharina Bringert from the University of Warwick, who does a lot of falling tower experiments, we wrote this book chapter. And actually, most catalysis, actually surprisingly to me, in space is done on recycling. So even enzymes are used there, but that is not the topic of today. Just to finish my introduction, we are very concerned with using the space resources because we cannot all bring up over there. So we have to use the moon to make medicines. And we have made a book chapter here, which is coming in the book of Melissa Swart. And that also inspires our space experiment, as you will see. And we have published, which is under review, on phosphate nutrient recovery, where we give quantitative information on space circularity. A lot of information is given on circularity, but far too less mathematical calculations, which really give evidence how we do it and how good it is. Now, just to round it up, we published a chronicle of spacecraft farming. And this is a table which is endless. So as you all know, a lot of experiments are done. So this is just until 1982, all space farms which have been made over there. And we gave some thoughts here on how can you increase the productivity, because as now you will have to bring 10 glass houses per astronaut, and very obviously this is not feasible. And exactly for this, we got the ARC Center of Excellence Plans for Space, which is University of Adelaide led, and I'm the program lead of the engineering part. And I also have as co-CI a discovery on space chemistry and 3 LEAF grants, which are related to that. And just to round it fully up, here's a review on plant stressors on space. The basic thinking is you have to accept that space is stressful, that it's a harsh environment, and you have to use it at your benefits rather than to fight against the harsh conditions. So that is given in this review. Now I come to space medicine in the rest of the 12 minutes. We managed to get this on the cover of ACS Medicinal Chemistry. And what you see on the right side is the original space experiment. It looks like an animation, but it's a photo. There was a University of Adelaide logo on it, and they forbid logos on cover. So we had to cover it with the tablets. That's why it looks as it looks. But the tablet photos are the ones which were in ISS and out of ISS. And you see our review given over there. Now, I'm a flow chemist, and if you know a bit about microfluidics, you know, we all like this lab on a ship idea, to have something which you should not take too serious, but to have something held in a hand. Actually, it's much bigger, but held in the hand is the way we sell it. And you have a whole chemical factory or analytical laboratory on it. And here's a nice Nature paper talking about this. So you make personalized medicines at a compact manufacturing station, and that's exactly what you need in space if you want to make medicines in space and not bring them up. Now, there are a lot of experiments done in space about the decomposition of medicines. And you see one in the middle that investigated maybe 35 medicines, so that was at least very comprehensive. And you see a color code, red and black. So one is for the medicines which turned out to be stable, and one is for the medicines which didn't turn out to be stable. So it's a mixed picture as to be expected. Some medicines are stable, some not. But definitely you cannot use any medicine on Earth longer than 1 year. If you look on the description, so if you go to Mars, which around about 3 years, we have to have medicines which live longer. So that motivated our experiment. And to show another literature experiment before coming to our results, the literature is mixed. Sometimes or often the flight experiments or the ISS are less stable than the control, as you would expect it from common sense, but there are also opposite results reported. And then it depends on the state of formulation, if it's a tablet, a semi-solid paste, or if it's a liquid formulation. So it's a complex picture. Now, to look about the future role of astrophysicists, and if there will be a doctor on ISS. We published a paper, and I'm a bit proud that is after 30 years, my first paper in the social Science magazine, and you will see it's made with Virginia Watering, who made this famous NASA ISS study. And we made, we interviewed all the big space players, say those SpaceX and the Blue Origin, those people, and we asked them, how do you see the role of an astropharmacist? And they gave some conclusions, and I highlighted this here in orange, which you see. Now, our experiment, and this is still listed on the NASA website, has this official title. We are motivated by iron oxide coated ibuprofen tablets, that's why they are red. And we made similar tablets, naturally not of the same quality. We also did it in COVID times with students who didn't feel the risk to come to university while the university was totally empty. We made it at May 2020, which naturally gave us serious limitations in this period of lockdown in whole Australia. Now, we made 3 concepts, and there's not time to go into detail. I mainly want to explain one protection concept, which is in the middle. So we just didn't look if the medicines decompose. We wanted to, because that we know already at the start of the investigation, we wanted to test concepts to stabilize them. And one is to coat with heavy atom molecules. Ideally, we would have liked to use lead or uranium, but that is not easily feasible. So we were happy to use iron oxide and titanium as relatively high molecular atoms. And they should actually prevent alpha radiation and to a minor degree beta. And with gamma, we don't really know, so they're probably not the right concept. So that was exactly what we were investigating at ISS, and we had 2 more concepts. Now with this, we sent 60 tablets up to ISS and 6 to the outer platform, which is called MISSE Station, M-I-S-S-E. And we try to make a little bit systematic experimental design. So the colors denote experimental groups, like varying the iron oxide content, which is given in red. And in yellow, you see varying the ibuprofen content. And we used all ingredients which we think they are available on Moon in one way or the other. Now, we packed those tablets in cells. We used an aluminum blister, like you get normal tablets. We know that stabilizes the tablets, but we thought we have to make the experiment realistic and not to make it unrealistic just to get scientific results, but to do it as it would have been done if it's used by astronauts. Now, I have also such a nice mission badge, which is here. So we used Northrop Grumman flight number 14 from Wallops Island together with Space Tango, and 1,000 thanks to Space Tango here. And we made a second launch even just shortly after for the outer station, Northrop Grumman 15, and again, not again, with, now it's with Alpha Space, who are now called AIChE Technologies. And here you see, again, this is not a fake picture, this is a real Adelaide sample moving around in the microgravity in the front of a US astronaut, and you see a picture of an astronaut at the outer MISSE station. Now, some results, we made results here on Earth. Luckily, we can simulate space in a way. We can also simulate space radiation. We looked on alpha particles, and you see a lot of number of peaks. This basically means the one ibuprofen peak has decomposed in many, many substances. So we did know ibuprofen is labile to alpha radiation. And we could also identify the samples by thin layer chromatography, and we found that one of the decomposition products is neurotoxic. So it's not only that the ibuprofen is decomposed, but you get something toxic if you would take it. Now, we looked also on beta radiation. I don't show the results here for reasons of time, but also with the colleagues at the Royal Adelaide Hospital on X-ray radiation. And there's a lot of information in the table. Just look on the right side. You will see that for different formulations, the degree of decomposition is up to 20%, but you also see that the experiments, which we repeat on ISS, have an influence. And that's exactly what we now found on ISS. So now this table is from ISS. You see the 5 experiments, which you have seen before in color. And if you look, for example, at a low iron content, and I marked this red, there's a significant decrease in the ibuprofen content. So this decomposed in the ISS. So normal ibuprofen tablets probably would decompose there because they don't have this iron oxide. The other tablets were all stable. There's a lot of scattering also in the results, not surprisingly under those COVID conditions. But the main result which we found was outside ISS on the meso station. You see it on the left side, and compared to inside, you see chromatograms, and the simple message is the more peaks you see, the more decomposed it is. And the main peak, the big one in the middle, is the ibuprofen. And you see on the right side all the decomposition peaks for the high dilution case, as we called it, and for the base case. Interestingly, we found iron oxide stabilizers inside and outside under the harsh condition. And surprisingly, we found flavors added, which were made only for curiosity from Nottingham. They stabilize it. That's why you make science, because you find something which is not according to the expectation. So it looks like, at least in this case, that flavors could stabilize it, and we have also an explanation for it. I'm on my last 2 slides, I think 3 minutes left. So I will not go over time. I like to do, and this shows a bit what we will do in the Center of Excellence, digital twin modeling. So we like to look what is the best mix of food to meet the nutrients of an astronaut. And then we put additional constraints, second and third principle. As you see, it should be circular. You could make it in not 50 glass houses, but maybe only in 5 glass houses, and so on. So we go hierarchically down. But the first thing the computer tells us out of 1,000 plants, which is the best combination. And we found this space salad here, which is made of 6 ingredients. I don't show them now for reasons of time. You see sweet potatoes are among them. And they gave the nutrient supply which an astronaut needs. If you don't consider meat, we also made simulations with fish and meat, but this is another topic. So I'm at the end of my talk, and this is a nice certificate which we got. It's really, even for me after 30 years science, impressive to have made a space experiment, and nice to know that until my pension, exactly in 7 years, we have this nice center of excellence, and I look very much forward to working on that, but also to working with all the colleagues here from Swinburne and so on. This fascinating space which was presented. Thank you.